about cosmological constraints, several cosmological constraints, which we have updated on neutrino physics, which is actually physics, which is physics beyond standard model. So these are my collaborators, my former PhD student and my PhD student now. All of us work in Institute of Astronomy and National Astronomical Observatory, which is belonging to the Bulgarian Academy of Sciences. So neutrino topic is very interesting because first it's a very important particle, constituent of the standard model of particle physics. Then we don't know fully its physical characteristics. So both concerning neutrino masses and also neutrino oscillation parameters. And of course, we are interested as astronomers and astrophysicists because these particles are produced in astrophysical sites like the sun, stars, supernovae, etc., and the early universe. So I will talk mainly about the cosmological effects of these particles in the early universe and the cosmological constraints which we can put on them. I will be interested mainly on sterile neutrino, which presents beyond standard model of physics in neutrino sector, and also on neutrino oscillations between active and sterile neutrinos. And if I have time, I'll discuss also some additional model with new interactions. The outline of my talk is presented here. So first, I'll say quickly several words about the neutrino influence on early universe processes at pre-BBN and BBN epoch. Then I'll say several words about BBN, which I added because I saw that here nobody talked about BBN, so I decided to just two slides presenting Big Bang nucleosynthesis as a probe of new physics. And then I will show you the update of different constraints on neutrino beyond standard model physics. First on neutrino oscillations parameters and on lepton asymmetry, and this is work in progress. And say several words about dark radiation problem and its connection with our findings concerning the interplay between neutrino oscillations and lepton asymmetry. And then finally, I will talk about the decoupling temperature of how we can find the decoupling temperature of sterile neutrino in case of some special case of new interactions, which we have studied. So in more detail, the model of BBN with neutrino oscillations, the update of this model we have provided with in work with Mariana Panayotova. Then the findings which concern lepton asymmetry and BBN with neutrino oscillations were given in, sorry here for the mistakes, in 2019, and we continue the work on this topic. And the results concerning the freezing temperature of the light sterile neutrino were given in this publication. And now we are working on a more precise 1% corresponding to 1% helium uncertainty. Also, I will show you preliminary results on that. And finally, the constraints on new interactions, which is a work in progress again. So what about neutrinos and their effect at the radiation-dominated stage in the standard model? There are, according to the standard model, the universe is filled with masses and non-oscillating neutrinos. You know, there are 3 neutrino flavors, lepton asymmetry is 0, and neutrinos have equilibrium Fermi-Dirac state. So the usual influence which neutrino have is the effect on the expansion rate of the universe due to the fact that they participate in this radiation content of the universe, so they influence the expansion rate. According to this standard model, if you change delta NF with an additional light particle, light that's with masses less than 1 MeV during the BBN, then you expect to increase the expansion rate of the universe. Another important factor, according to the standard model, is that at the temperatures much higher than 1 MeV, there is neutrinos are kept in equilibrium due to these processes with particles from the plasma. At approximately 2 MeV, their rates become comparable with the expansion rate, so they decouple. And since then, these decoupled neutrinos were free streaming. So besides all this, during that same epoch, around 1 MeV, electron-neutrino effects nuclear kinetics in pre-BBN epoch. So I will talk about that in more detail. That's why I don't show it here. And finally, you have some heating due to the electron-positron annihilation at this epoch, according to the standard model. And we expect cosmic neutrino background with a slightly lower temperature than the CMB1. So when you include oscillations into the standard model, and you know that they're experimental fact now for the flavor neutrino oscillations, then picture changes a little bit. However, when you discuss only flavor neutrino oscillations, they do not affect considerably BBN. So what people studied since the 90s are the flavor sterile neutrino oscillations. They can affect nucleosynthesis. And first I will flash several effects, and then I will tell you how they affect BBN. So the first thing is that flavor sterile neutrino oscillations can excite additional light particles into equilibrium, so influence, increase the expansion rate. This is the most important effect for neutrino oscillations effective before decoupling of neutrino, and it was first studied in the paper Dolgov in the early 80s. Then when you consider oscillations effective after active neutrino decoupling, it is possible that for certain oscillation parameters, that the strong distortion of neutrino energy distribution can appear, which leads also to depletion of neutrino number densities, which means that this can change considerably the weak interaction rates during BBN, in BBN epoch. And that's why this is interesting from point of view of putting constraints on these oscillation parameters from BBN. So we have discussed these cases. And finally, another effect is the possibility oscillations to change neutrino-antineutrino symmetry. This was first mentioned in Fudolko's papers. We also worked on that case. So to resume, active sterile oscillations may have considerable effect, cosmological effect, and therefore you can put very stringent constraints on oscillation parameters. So the evolution of neutrino in the presence of late oscillations is given by these equations. I will not go into detail. If someone is interested, I can discuss it later. But what is important is that these equations are for the raw matrix, density matrix of neutrino and antineutrino, and they account simultaneously for the expansion rate, for the oscillations, and for forward scattering of neutrinos. And the interactions, weak interactions, are negligible because we discussed the case when neutrinos have decoupled already from the plasma. So you can follow the evolution of oscillating neutrino. Which is important here is that due to the fact that you expect strong spectrum distortion, you need to describe the distribution of neutrino. And we have found that for non-resonant case, thank you, around 1,000 bees are necessary for that. And for the resonant one, around 10,000 are enough. So in fact, instead of two equations and integral differential equations and one for the nucleon densities for BBN, you must solve thousands of equations, and this makes the numerical task very complicated. Let me say just several words for the standard Big Bang nucleosynthesis. Why it is so important probe for the very early period of the early universe. It is such because it is at present Big Bang nucleosynthesis is parameterless theory. It has three main parameters, and they have been already determined very precisely. I have written here the complete parameters. So here you see an illustration of calculation of the evolution of different elements during BBN, and there are nice codes, precise codes, and theoretically calculated abundances of light elements which are produced during BBN are in very good agreement with the observational ones. Therefore, it is possible to use, and it has been used for many years, for 30, 40 years, as a reliable test for physics during the conditions of the early universe, and also test for beyond standard model physics. People make models and try how they affect BBN, and from a BBN they put constraints. Now I will show you our constraints. The preferred element is helium-4, so we use helium-4 for putting constraints. Recently, this element was determined with much better precision than before. That's why we decided to re-examine all our models, and all our constraints, which we have obtained concerning sterile neutrino and active sterile neutrino oscillations. So now we have measured helium-4 with 1% precision, and we use this precision to obtain constraints first on neutrino oscillation parameters. So that kind of equation governs the evolution of nucleus in the presence of electron sterile oscillations, which we discussed. The only difference from the classical one is this term here, where enters the raw matrix of neutrino, oscillating neutrino. Otherwise, it's the classical equation describing the evolution of nucleus. So we have solved it for different parameters belonging to our model of late oscillations, from the temperature range from 2 MeV to 0.3 MeV. We have calculated helium and the produced helium-4, and compared it with and found the 1% precision for making the for attaining the constraints. Here you see previous constraints at this plot. So starting with the 90s, when the precision of helium was between 3 and 7%, or at least we believed it is like that, then people found that actually systematic errors are much bigger than belief, etc. People obtained constraints on the mass difference and mixing angle of these oscillation parameters. So you see here different curves. First, in 91, the account for depletion of electron neutrino was provided. It corresponds to this constraint. Then people tried to account for the spectrum, but in one a momentum approximation. You see here the work of Enquist et al. And our results of 20 years ago are here, given here. And this better constraint by approximately an order and half magnitude at maximum mixing was achieved due to the fact that we accounted for the spectrum distribution of neutrino precisely, as I have shown you in our previous picture. So these are the results of Dolgov and Villante from 2003. I've given them here because we discuss our better results are here, but they concern only electrostereo neutrino. Thank you. While the other we haven't studied. They studied muon stereo neutrino as well. And here are the updated BBN constraints on neutrino. This is the curve which corresponds to 1% precision for helium. So this is the most precise constraints which we have today. Okay, they are based on numerical analysis of more than 100 BBN models. And this analysis was mainly done by me and Mariana. Also, it is interesting. So this constraint corresponds to the assumption that initially the sterile neutrino was 0. So it was not filled at all. If you allow for the sterile neutrino to have some initial population between 0 and 1, not full because it's forbidden from cosmological considerations, then these constraints change a little bit. So I don't have time now to show you and to explain that, but these changes can be different, either strengthening or relaxing the constraints, depending on the fact how the sterile neutrino, the presence of the population of sterile neutrino, influences the plasma. So it has two effects: dynamical, increasing the expansion rate, and also kinetic effect. It can suppress the kinetic effect of oscillation. So depending on which one dominates for the different oscillation parameters, you can have relaxation or a strengthening of the constraints, as you see here in illustration of from our previous works. And now we have obtained the constraints corresponding to delta NS 0.2, which is the contemporary limit which we have on the additional light neutrino particles. And here this curve corresponds to this case in comparison with the one for delta NS 0. Okay, so I will not discuss lepton asymmetry because of the lack of time, but I will say just several words concerning neutrino with lepton asymmetry. Besides the well-known effects of lepton asymmetry discussed in works of standard BBN, etc., and standard cosmology, there is also the possibility of indirect kinetic effect of very small lepton, tiny lepton asymmetries through oscillations. So the presence of lepton asymmetry can change neutrino, antineutrino number densities. It can change neutrino and antineutrino distribution, and also the pattern of neutrino oscillations. It can suppress or enhance oscillations. And what I wanted to stress here is that this possibility of lepton asymmetry to suppress oscillation can be used to solve the so-called dark radiation problem. So what we have found is a connection between the value of lepton asymmetry and oscillation parameters from our numerical studies of BBN with lepton asymmetry and oscillations. And you can apply it to solve this problem of excess radiation density, which consists in the following. There are experiments, oscillation experiments, which hint to oscillations between sterile neutrino of the EEF mass with the electron neutrino. I have listed them here. But these kind of oscillations with approximately big mixing, they lead to these oscillations with such large mixing and EF mass, because some of them suppose 0.1 eV, some of them 10 minus -2 eV. So different mass differences, but all they, with large mixing, which they suggest, lead to thermalization of the sterile state. So that means they lead to one full state, additional state, okay, at the BBN epoch, which is absolutely forbidden as far as we have this strict constraint. So one possible solution is that lepton asymmetry that can suppress oscillations actually it does not allow for this sterile neutrino to be thermalized during BBN, so there is no contradiction between BBN and the observation of this excess radiation density. Besides our ideas discussed in 2012 and 2013, there were also analysis of Hannestedt and Merisi, etc. Okay, so I'm sorry, I will not talk about sterile neutrino freezing. I will just show you the numbers. So the old estimation was that it should be larger than 130 MeV, and now based on the new results, new constraints on the delta NF from BBN, we have put much higher limit for the decoupling temperature of the sterile neutrinos. It's around 315. This is what which I make with Emmanuel. And the constraints on new interactions, you can look at the site of the conference. It's an interesting model. It was even checked at Atlas by Atlas collaboration at CERN. And we have very, very strict constraints on the strength of this type of new interactions on the basis of BBN and assuming interaction between sterile neutrino, right-hand neutrino, and this new particle, the channel tensor particles. Thank you for the attention.